This lecture video will cover some aspects of the computer architecture. So we mentioned last time these aspects very briefly, and now we will look at a couple of blueprints for computing devices in more detail. In general, we will continue on the topic of computer architecture in general and how physical hardware is used to realize software code in practice. We will also look at machine code, actual symbolic machine code, also known as assembly code, and we will review what assembly code looks like and how an assembler produces that code. So last time we looked at the very big picture of computing, which more or less looks like this. So we have software code, the code that most of us can write, which is very high level, such as this high level code on the left. Software code itself is abstract. It doesn't convey any meaning about how some text appears on the screen or which particular bits the processor has to physically manipulate. On the other hand, at the other end of the spectrum, on the right side of the picture, the CPU, the processor, is a physical thing which it turns out it cares a lot about the particular bits and bytes. And the CPU can only run very low level code. In particular, it will only work on ones and zeros. So you on the very low level, the CPU can only process code like this. So the fundamental question here is how does the high level software code get translated into something that the CPU understands? The other big picture from last time is the software hierarchy of a computer system. So at the lowest level, right here in the picture, there is machine code. So machine code is the lowest level of the software stack. Those are the raw bits that control what the CPU is doing. So that's binary machine code. Of course, plain bits are not human readable, so we have to make those bits represent something. And in order to write code that controls what the CPU is doing, we do not want to write the code using ones and zeros only. For the same reason, binary numbers are not human readable. So instead we rely on a tool called the assembler. So when working with a microprocessor on a very low level programming, what we do is we write code using a symbolic machine language, something that is very low level but still human readable. And this symbolic machine code is also called assembly language. And the assembler is a program which translates assembly code into that raw machine code, into those raw ones and zeros. And of course, for the same reason that we have the assembler, we have built more software abstraction on top of the assembler. So that would be the levels in between the low level and high level right here. So in assembly code or in this symbolic machine language, it's possible to have directly control of what the hardware is doing. So you can tell the CPU to do something, or you can place certain bits in the memory. And in most cases, especially when doing high-level programs, this is not needed, and it's possibly unsafe for an inexperienced programmer to manipulate hardware resources directly anyway. So instead of writing something on a very low-level symbolic machine code, high-level programs interact with an interface that is built on top of the machine code, and this interface we could call a virtual machine. We have already seen what virtual machines can do in the previous computing courses, so you can run programs and operating systems even in a virtual sandbox that is all software. Hence why it's called a virtual machine. From a system perspective or an operating system perspective, this kind of virtual machine abstraction makes a lot of sense, because at the end of the day, only the operating system really needs to interact with hardware. All other programs are managed by the operating system. So what our operating systems do, they provide a virtual sandbox for all the other application programs to run on. As discussed in the previous lecture, one of the great ideas behind computing, what makes a computer, is its versatility to run different software programs. So the basic idea is pretty simple, this stored program concept. So the computer is just a fixed hardware platform that can execute different instructions, so the lines of code dictate what the computer is doing at a given time. And this is what is actually called programming. So program code is written and stored in the computer's memory, just like data, and that then becomes what we know as software. At the heart of the stored program concept, there is the von Neumann machine, so the generic blueprint of how a computer's processing unit, the CPU, actually is constructed. So the idea here is that in the computer's memory, you do not store only the data that is being manipulated, but also the instructions that tell the computer what to do. And of course, in practice, modern CPUs are more complicated than this, but the basic principles still apply. So the computer or the computer's processor is still consists of some processing unit and some memory, and in the memory we have both program code and data that these programs manipulate. In particular, in the memory of a von Neumann machine and in the memory of all modern computers, there are those two types of data. So there's the data and the programming instructions. And despite their different functions, though, both are represented as binary numbers that are stored in the same generic random access structure. What random access means is it's a continuous array of memory cells of some fixed width. These are usually called words or locations, and each has a unique address. And if you know the address, you can pull up some piece of data from the memory. Now, data memory consists of those high-level programs that manipulate abstract artifacts like variables, arrays, objects, things that we create as programmers. When translated into machine language, these data abstractions become a series of binary numbers that are stored in the computer's memory. The instructions themselves, when translated into machine language, each instruction, each line of code becomes a series of binary words or binary lines of binary numbers representing some machine language instruction. And at each step of the CPU's operation, it fetches or reads some word from the instruction memory, decodes it, executes it, and then figures out which instruction it should execute next. The machine instructions that the CPU can execute, well, they can perform many things. They can do some calculations, they can read and write values to and from the memory, and you can also conditionally jump some lines of binary code to execute other instructions or other parts in the program. How the CPU executes these, it uses three hardware elements: an arithmetic logic unit or an ALU, a set of registers, and a control unit. Now the ALU is basically the unit that performs all these low-level arithmetic and logical operations. A typical ALU can add two numbers together, test whether a number is positive or negative, manipulate some bits in the memory, and so on. Registers are memory slots that are very close to the CPU. So basically they exist in order to boost performance. It's desirable to store results of the operations that the CPU is performing close by, rather than shipping them in and out of memory. So that's why every CPU is usually equipped with a small set of high-speed registers, each capable of holding one single word. So if you, from the previous slide, you remember this word length, basically how long those instructions or data items are. Usually they are 16, 32, 64 bits wide, which is why we speak of, in modern times, we speak of 64-bit processors, for instance. The final item, the control unit, basically decodes all of these instructions. So as the instructions are represented in binary code, before something can be executed, it must be decoded, and based on this instruction, the ALU will be able to do something. So the control unit simply feeds instructions to the ALU from the registers and the memory. Of course, the programmable computer could not work without having some wiring between these different components. So data buses, represented here in blue, green and orange, connect these different components, which allows the control unit to read and write data onto the different hardware components. These data buses sometimes carry data, sometimes memory addresses, sometimes instructions through through them, and these instructions and data has to do with numbers and memory locations, and this in turn is software on the lowest level. Basically data, how to process it and where to store it, and that is basically the lowest level of computer programming that there is. Now that we understand more or less how the computer's processing unit is constructed and why it works the way it does, let's look at actual assembly code next. So what does this low-level symbolic instruction set or symbolic instruction code actually look like, and how is it constructed from higher level code? So just to pause to think about where we are right now. At this point, we have some idea about how computers are actually constructed. We have an idea of how the computer executes commands. Still, we have no idea, at least not yet, how the computer chooses what operation, what pieces of code it will execute next. This is important because most computers are able to run multiple programs at the same time. So how does the CPU actually decide which program's code it's executing at a given time? But we will dedicate some time for discussing this in the next couple of weeks. Before that, let's talk briefly about how this high-level code is actually transformed into the set of instructions that run in some process that the CPU is able to execute. Low-level code, assembly code, or otherwise known as machine code, is very low level and usually fixed with the capabilities of the CPU. So basically what this low-level code does is using it you can do some basic arithmetic, so mathematical operations, and then manipulate some bits or will manipulate numbers in the memory and registers, and that pretty much is it. So it's not very complicated. So we could have, for example, some assembly code like this. We don't need to go very detailed into what this actually does, but this is what it looks like. So at this point we could have assembly code like this. So what do we actually do with this code? So remember, again, this is the lowest level of computer programming, yet this is still not in a form that the CPU is able to execute. So we have to do something to this code to get it running. So in order to solve this problem, we need a program called an assembler. So basically, when we talk about assembly and an assembler, we are basically answering to the questions: how can we turn this high-level program code into binary machine language that the CPU is able to run, and how does whatever that code has in it end up on the user's display? So how does the code actually do anything? To recap a little, assembly languages are symbolic machine languages. There exists more than one assembly language, as it is tied to the CPU that you have in your computer. So different CPUs have different machine instruction sets, and therefore different assemblers and assembly languages. So if we begin by examining the software hierarchy from bottom up, then the assembler is the first step above hardware. This is as close to programming on the hardware level as possible. Sometimes you might think this is never going to be something to use in practice, because very few of computing professionals will actually need to be able to write assembly. But if we are thinking about how the computer works and the environment in which an operating system works, this is the first step towards understanding how the computing systems actually operate. Let's dedicate a few moments for discussion about how these electric circuits, that is the CPU, comprised of logic elements, logic gates, are weaved together with programming. So at this point it should be clear that buses that move data and instructions between the different hardware components are, in a very simplified way to say it, electrical cables where current moves. The main operating principle of the computer is basically that it is easy to represent numbers using electrical current. We represent ones with an electric signal and 0 with no electric current. So this is how we build a signaling machine. So this is why you deal with binary numbers and calculating with them in the basic math courses. The instruction memory in a computer is a chip which pushes binary operating instructions to the processor one at a time, or to be more pedantic, the processor actually fetches instructions from the memory one at a time. And also, it's not important at this point to consider how the chipset is actually built or how the input devices work. What we want to understand is how these elementary logic gates form larger memory modules. Once we have constructed some memory, so we have put these building blocks, logic gates together, and we have wired them together with buses, then we have some memory. So we can store data in these memory modules. And then we need to store data in the memory. And in order to map variables into slots in the memory, we use something called a symbol table. In the most basic computer, a read-only memory chip for instruction memory houses the machine code in a binary format. Again, in a modern computer, instructions are not in a read-only memory chip, but we can think of this memory module for now, for simplicity's sake, as something that is pre-written with all the instructions that the computer needs to execute. Anyway, because the processor, this logic chip, understands the meaning of these binary codes, those binary codes then make real things happen. And now these binary codes, this binary machine language, is a collection of agreed upon generic rule-based instructions, and knowing what each instruction does enables us to program the microcomputer. And again, we don't actually need to care about what type of a chip the processor is. It suffices if we understand it as a pile of logic gates and flip-flops and switches, transistors or multiplexers all together. So if we take this ROM chip to store some program code, we could write binary code directly onto it, and the processor would then understand, well, it would then start to execute that code. Of course, programming using only binary numbers could be painful, to say at least. So that's why we use assembly language, a symbolic machine instruction language that basically allows us to translate a very low-level programming language into binary codes. So for example, consider this binary code here, which in assembly language translates to an instruction to add two numbers together and store the result in a third memory location. So probably in this very made-up example, this command to add will take variables R1 and R2, or values from registers R1 and R2, add them together and store the result in R3. Anyway, this is a completely made-up example just to demonstrate how this translation between a binary number format and a symbolic machine language format is done. So machine instructions are just instructions in binary numbers in a very specific format. And maybe we could interpret these binary codes from a language where the same instructions are put in a more human-friendly form. So this is basically what the assembly language is. It's an English version of raw binary machine code. So what assembly language and symbolic machine languages are in general is a more illustrative, more human-readable format of the binary machine code. Why we needed it, basically they defined the format for the machine language, which is more toward natural languages. An assembly language has the same structure and commands as the binary code. It's just easier to read because, well, it's written in text format. And in addition, memory addresses can often be referenced by using names or variables, while leaving the actual reference to a memory slot to be defined by the assembler program that will then generate the binary version of the code. Something to keep in mind is that these machine languages and assembly codes are always tied to a certain type of a processor. So there exists different assemblers and different assembly languages depending on the type of the processor. The only real challenge is translating this machine language. So in assembly, you usually have some way of using symbols that reference the memory addresses. These, in more familiar terms, are called variables. There are no variables in the way of what a variable means in a high-level language in assembly or in binary machine code. So variables are just literal references to memory addresses. And again, in order to map these variables to actual memory addresses, the assembler needs to keep track of them using a symbol table. So given that you are writing assembly instructions that the assembler understands, and the assembler is also keeping track of where values and variables are stored in the symbol table, then this symbolic machine language can be translated into binary machine language. And the process of this is called assembly, and the program that does this is called the assembler. The assembler is basically a translator program. That's why you hear both assembly and assembler as terms related with assembling code. So this again is the first step in a computer's software hierarchy from the bottom up, and at the same time it's also the first abstraction layer above hardware. Above the assembler there's a lot of different software abstractions, but the assembler is the layer that everything else is built upon. The assembler in practice is just a program which follows certain simple translation rules to transform these symbolic instructions into binary instructions or binary code. The assembler reads a text file full of code in the assembly language and produces a binary counterpart for the file. The binary file can then be executed by some computer, and in here I have written can be executed by any computer. So the keyword here really is any. So the idea with these binary programs is that they can be moved from computer to computer, given that these computers have the same type of a processor. So once the assembly process has been done, and we have a binary version of software, it should work with any computer with the same type of a processor. This is also incidentally why sometimes program files are called binaries. And how does all of this fit in the big picture? So why exactly does the symbolic machine language even exist? Well, as said before, programming in machine code has to be done at some point when we transition from software to hardware, but we want to do this in a human readable format, so therefore assembly language exists. Programming in assembly means you understand exactly what is happening on the hardware platform, still without having to program everything in binary code. Assembly languages are still very, very low level, so they are one-to-one comparable with the binary machine language and its features. What sort of program is the assembler anyway? So in order to build a computer system, we need an assembler. So let's say we have just built a computer from scratch. At that point, the only way to control the computer would be to write binary machine code, which in the long run might become tedious. So therefore the solution is to use another computer to write an application, the assembler, which is able to translate higher level assembly code into binary code. So the best way to think of this is that we're not building the first computer in the world from scratch, but we are perhaps building the second or the third computer in the world. If we already have a programmable computer which can be programmed in a high-level language, then a translator from assembly to machine code would be an easy task to do. And in this analog, this binary application code is produced by a different computer than what is where it's intended to run the code. But of course, in practice, if we were to write assembly code, which in one of the exercises you are asked to do, then we are also executing the code on the same computer as well. When we say we could easily build an assembler, I really mean it. So the assembler is in reality is a very simple program. It basically repeats one loop of operation. So it begins by reading an assembly language instruction from a text file. Then it separates the different parts of the instruction from one another, finds the binary equivalents for all parts of the instruction, joins the binary instructions together, and writes binary into an output file. For example, let's look at a instruction that could be something like this: load the number or value 18 to register R1. Again, this is a made-up example. So we could read something like this from the text file where the assembly code is. So right now it's not even important to understand what this instruction does. It's enough just to get this stored in some table structure, and we need to figure out what these parts are in this instruction. So load needs to be differentiated from R1 and 18, and then we have to find the binary counterparts for these parts of the instruction. So the first step would of course be to take this line that we have just read and split the different parts in the instructions. So that load, R1 and 18 are all different yet equally important parts of this individual line of code. Once we have figured out what the individual parts of the instructions are, each of them are translated into their equivalent binary codes. And this translation is done by using the specification of the binary instruction set. In practice, what the specification of the instruction set is, it's a really long manual listing every single binary instruction possible that the CPU supports, and their equivalent binary codes. Numbers, registers, other constants depend on the machine language and the processor. In our example, it could be that 18 is represented as a binary number, as the binary number 18, or it could be represented in a different way. This always depends on what platform you are using. This is the only part during the translation when we need to figure out what to do with these human readable codes and what they mean in binary. At other times we don't need to care anymore. And the last step in the process is to join all these individual parts of this instruction together. So once we have figured out the binary equivalents of the individual parts, then join these instructions together. It's possible that not all binary parts are equally long. In that case, we need to add some extra padding, so blank zeros into the binary code that does nothing, or something else. Again, depends on the actual instruction set. Assembly code does come with some peculiarities. So, for example, some code block symbols or labels in addition to variables. These could turn tricky in this translation, but this is not important to consider for the big picture. In the real world, however, using real modern computers, there are some points to consider how things work in the real world. Our example there was just imaginary. So, first of all, simple instruction sets do not need a complex assembler program. Although complex assemblers might support multiple simple languages, and assemblers for complicated instruction sets are always more complicated. Some assemblers have built-in symbolic variables for programming convenience that work with arithmetic with constants. So for example, you could have a variable name such as array, and you add some constant number, let's say 5, to it, meaning that you want to point to the 5th memory address from wherever this array points to. Another real-world complication could be that assemblers usually allow you to write using macros. So for example, you can write small functions that shorten code if it happens many times in the program code. The cost of using macros is cheap, therefore these kinds of macros in assembly make sense. Finally, it's not very common to use a standalone assembler. So the assembler usually is bundled with some other code compiler. So for example, in the Linux and Unix environment, when you program with the C or C++ programming languages, you use the GCC compiler, and in that bundle there is an assembler program called the AS. Assembly code is rarely written by hand. Instead, these high-level language compilers translate assembly from a high-level language. Because this compiler is a program, it's a machine, it doesn't need to bother writing symbolic machine instructions. It can write binary directly from a high-level language. On the other hand, many high-level languages make it possible to write what is called inline assembly code. So writing assembly code within another high-level language. This is commonplace, for instance, when using the C programming language. This gives a C programmer very big optimization possibilities when you can directly access some features of the hardware below. Finally, what do I need to remember from this lecture? So we went through this big picture of how computer programs are realized and the basic computing architecture, the basic layout of a CPU. Then we looked at what the assembler, assembly instruction set, and the difference between these two, and how the assembler works.